A Mode 16 counter uses 4 JK flip-flops as diagrammed here. In this circuit, the output at Q becomes the clock input for the next JK flip-flop. Each JK flip-flop is open, thus they are set automatically to high or 1, which keeps them in their toggle position. The counter starts at 0, 0, 0, 0. As pulse 1 arrives at the clock input at flip-flop 1, it toggles on the negative edge. The output at Q1 will go from low to high or 1, thus the counter will be at 0, 0, 0, 1. When clock pulse 2 arrives at flip-flop 1, it returns output Q1 back to 0, which causes flip-flop 2 to toggle to 1. The output at Q2 is 1, and the count on the display now reads 0010. The counting continues, with each flip-flop output triggering the next flip-flop on its negative going pulse. The 1's position, or A, must change its state on every count. Thus, flip-flop 1 must toggle for each clock pulse. The 2's position will change its state half as often as the 1's position. Thus, flip-flop 2 will only toggle half as much as flip-flop 1. The 4's position will change less often than the 2's position, and the 8's position less often than the 4's. Thus, each more significant bit will toggle fewer times. Let's observe how a sequence of 10 clock pulses will ripple through a series of 4 flip-flops in this 4-bit counter. As we have shown, the first clock pulse generates a binary output of 0001, and the second, an output of 0010. As the remaining pulses arrive at the input, the third pulse toggles Q1 back to 1, with Q2, Q3, and Q4 remaining unchanged, and the output is 0011. Pulse 4 again toggles Q1 back to 0, with Q2 toggling to 0 and Q3 to 1, with Q4 unchanged, and the output is 0100. These toggling patterns, triggered on the negative edge of the clock pulse, continue, with pulse 5 giving an output of 0101. Pulse 6 outputs 0110. Pulse 7 outputs 0111. The 8th pulse results in an output of 1000. Pulse 9 a 1001. And finally, as expected, the 10th pulse toggles the appropriate flip-flops to give 1010. The digital memory storage and bit shifting characteristics of the shift register is essential in many digital electronic systems. The keying of numbers into a calculator demonstrates the practical application of a shift register. As numbers are entered, they are stored and displayed. Each subsequent number that is entered shifts the previously entered number to the left. Let's look at how a shift register operates by observing the shifting of an 8-bit register based on a series of binary data inputs. We have 2 serial inputs, D1 and D2, arriving at an AND logic gate. A master reset input at MR, which when activated by a low or 0 input, will override all other inputs and reset the Q1 through Q7 outputs to 0. A clock pulse input, CP, which will be enabled when transitioning from low to high. The right-pointing triangle symbol without the bubble signifies this clocking functionality. Let's input the binary data at D1 and D2. With an AND gate, when both inputs are high, the output is high, and conversely, when either inputs are low, the output will be low. At T1, the 0 or low at MR overrides the D1 and D2 inputs and sets all outputs to 0. At time T2, D1 and D2 are high or 1. Thus, the output at Q0 is 1. This information bit is placed in the Q0 position in the register. This shifts the other bits one place to the right. At T3, the input of 0 at D1 and 1 at D2 results in an output at Q0 of 0. The 0 at Q0 replaces the 1, again shifting all the bits one position to the right. The 0 and 0 input at T4 again outputs a 0, which drops into the Q0 position, shifting the bits again to the right. At T5, the input of 1 outputs a 1 that drops into the Q0 position, with the bits shifting again. The inputs at T6 produce another output of 1, which shifts the bits again. This continues for clock pulse T7 and T8, with the inputs at T7 and T8 resulting in zeros at output Q0. This input into the register continues to shift bits to the right.